Have you ever thought about a phone that you could fold up and put in your pocket? Or, clothes that could charge your watch while you walk? These amazing ideas are getting closer to reality every day, and it's all thanks to something called flexible batteries. Unlike the stiff, blocky batteries in our phones and laptops right now, flexible batteries can bend, twist, and stretch. This incredible ability opens up a whole new world of possibilities for technology. We could have medical sensors that stick to our skin like a bandage, or wearable gadgets that are truly comfortable to wear all day long. But before these cool devices can become a part of our lives, we have to be sure their batteries are safe, reliable, and strong. Making a battery that can bend is one thing, but making sure it works well after being bent 1,000 times is a whole different challenge. That's where testing comes in. It's like a fitness test for batteries. Scientists and engineers put these flexible power sources through a series of tough workouts to see what they're made of. They need to know how much energy a battery can hold, how quickly it can deliver that energy, and how long it will last. This isn't just about performance, it's about safety. A battery that fails could be dangerous, so rigorous testing helps us build better, more dependable power for the amazing flexible gadgets of tomorrow. Think about it this way. You wouldn't want your roll-up tablet to stop working just because you rolled it up too many times. You also wouldn't want the battery in your smart shirt to get too hot. By testing these batteries in every way we can imagine, we are essentially building a rulebook for how they behave. We learn their limits, their strengths, and their weaknesses. This knowledge is super important because it guides us in designing better materials and smarter structures. It's this careful, step-by-step process of testing and improving that will turn science fiction ideas into everyday technology that we can all use safely and confidently. So, the journey to creating these amazing new devices is paved with careful experiments. The importance of testing cannot be overstated. It is the bridge between a brilliant idea in a laboratory and a useful product in your hands. Every time a scientist runs a test, they are gathering clues that help solve the puzzle of creating the perfect flexible battery. They are looking for ways to make them hold more power, last for more bends, and operate without any risk. This crucial work ensures that when the next generation of bendy, foldable, and wearable technology arrives, it will be powered by batteries that are as resilient and revolutionary as the devices they energize. So, how do scientists actually test these bendy batteries? It's a bit like a doctor's visit, with several different checkups to get a full picture of the battery's health. The first step is often a preconditioning test. Imagine a brand new battery is like a sleepy person who just woke up. It needs a moment to get ready for the day. This test wakes up the battery by gently charging and discharging it a few times. This process helps remove any tiny blockages or barriers that might have formed inside when the battery was made, ensuring that all the energy-storing parts are ready to go for the real tests that come next. After the battery is awake and ready, it's time for a relaxation test. This might sound funny, but it's very important. Scientists let the battery sit and do nothing for a little while. This rest period allows the energy inside the battery to spread out evenly. If they tested it right after charging, the measurements might be a little off, like trying to measure your height while you're still stretching. By letting the battery relax, they can get a true and fair measurement of its voltage, which is a key indicator of its health. This step makes sure all the following tests are accurate and reliable. Next up is the capacity test, which is one of the most important checkups. This test answers a simple question. How much energy can the battery hold? Scientists fully charge the battery and then carefully drain it, measuring exactly how much energy comes out. Think of it like filling a water bottle and then pouring it into a measuring cup to see how much it held. This tells them the battery's total energy storage, or its capacity. They might repeat this test many times to see if the battery's capacity fades over time or after being bent, which tells them how durable it is. Finally, we have the OCV-SOC test. OCV stands for open circuit voltage, and SOC stands for state of charge. This sounds complicated, but the idea is simple. It's like creating a fuel gauge for the battery. Scientists measure the battery's voltage at different levels of charge. For example, at 100% full, 90% full, 80% full, and so on. This creates a map that connects the voltage to the amount of energy left. With this map, a device can accurately show you if your battery is full, half empty, or about to run out, just by looking at its voltage. It's essential for creating a useful and user-friendly product. Once we know how much energy a battery can hold, we need to find out how well it can deliver that power. That's where the power and impedance test comes in. Power is all about speed. Can the battery deliver a lot of energy very quickly? This is important for devices that need a sudden burst of energy, like a camera flash. Impedance is a word for resistance. It's like a roadblock for electricity. A battery with low impedance can deliver energy easily, while a battery with high impedance struggles. Scientists measure this by hitting the battery with short, powerful pulses of electricity and seeing how it responds. This helps them design batteries that can power demanding gadgets. To get an even deeper look inside, scientists use a super cool technique called impedance spectroscopy. This is like giving the battery an ultrasound. They send tiny, harmless electrical signals of different frequencies, think of them as different musical notes, through the battery. How the battery responds to each of these different signals tells a detailed story about its internal parts. It can reveal problems that other tests can't see, like rust-like buildups on the electrodes or issues with the electrolyte, the liquid that helps energy move around. This test is a powerful tool for diagnosing problems and finding ways to make the battery work better. All these tests generate a lot of data, numbers, charts, and graphs. But what does it all mean? The next step is performance model verification. Scientists often create computer models, or simulations, that predict how a battery should behave. This step is where they check if their predictions match the real-world test results. If the real battery performs exactly as the model predicted, that's great. It means they have a good understanding of how it works. If the results don't match, it tells them their model is missing something, and they need to go back and figure out what it is. This helps refine their understanding and build better models. Together, these detailed tests are the secret to building better batteries. By finding the roadblocks or high impedance, we can change the materials to make electricity flow more smoothly. By watching the capacity fade over many cycles, we can develop stronger components that last longer. By using spectroscopy to spot tiny internal problems, we can prevent them from happening in the first place. Every test is a clue. These clues help scientists solve problems, improve the battery's lifespan, and, most importantly, ensure the battery is safe for everyone to use in all the exciting new flexible devices on the horizon. The world of flexible batteries is moving incredibly fast, but there are still some challenges to overcome. One of the biggest hurdles is making all this testing faster. A full set of characterization tests can take days or even weeks to complete for a single battery. Scientists and engineers are working hard to develop new methods and smarter equipment that can gather the same crucial information in a fraction of the time. Speeding up this process will allow them to test more new ideas and innovative materials, accelerating the pace of discovery and bringing better batteries to us sooner. It's a race against time to power the future. Another major challenge is finding the perfect materials. A flexible battery needs materials that are not only great at storing and conducting energy, but also incredibly durable. They have to withstand being bent, stretched, and twisted thousands of times without breaking or losing their performance. Researchers are exploring all kinds of amazing new substances, from special polymers to nanomaterials like graphene. Testing is essential in this search. It helps scientists quickly identify which materials are strong enough for the job and which ones need more work, guiding the way toward creating batteries that are both powerful and practically indestructible. Even with these challenges, the goal is clear: to make flexible batteries that are not only high-performing, but also completely safe. The detailed testing we've talked about is the most important tool we have for ensuring safety. By understanding how a battery behaves under stress, how it ages, and what its failure points are, engineers can build in safeguards. They can design batteries that won't overheat, leak, or cause problems, even if they are damaged. This focus on safety is non-negotiable, as it builds the trust we need to welcome these new technologies into our daily lives, from our clothes to our medical devices. The future is bright, and it's also bendy. With every test that is run and every improvement that is made, we get one step closer to a world full of amazing flexible electronics. Better and more efficient testing methods are leading to breakthroughs in battery chemistry and design. Soon, we will have longer-lasting, faster charging, and safer flexible batteries that will power a whole new generation of technology. From foldable phones to smart textiles and beyond, the careful work being done in labs today is unlocking a future where our devices are as flexible and dynamic as our lives.